in this video, we're going to summarize the different types of bonding that we have looked at and the structures that they adopt, and also then compare the different physical properties that each structure will adopt. Okay, the first type of bonding that we looked at was metallic bonding. And metallic bonding is the type of bonding that metals will adopt. So if I just bring back the periodic table, so anything on the left hand side of this step over here, anything on the left hand side is a metal. So all of these by themselves will adopt metallic bonding. Okay, so for example, sodium by itself will adopt metallic bonding, vanadium by itself will adopt metallic bonding, and so on. Okay, and you need to remember the definition of metallic bonding. It is the strong electrostatic attraction between fixed positive ions and the sea of delocalized electrons. So whenever you're doing the structure of metallic bonding, it is fixed positive ions in this lattice. So lattice just means a repeating pattern. So these positive ions are in fixed positions. Okay, and we have a sea of delocalized electrons, or just delocalized electrons is fine. The delocalized part is more important. That means that they are free to move. And metallic bonding is therefore the strong electrostatic attraction between positive ions and delocalized electrons. Okay, in terms of explaining the structure of this, so you've defined the bonding. Metallic bonding, or metals, will always adopt a giant structure. So we're just going to kind of cover these over here. They always adopt a giant structure. So we tend to call it giant metallic. And what that means is that this pattern over here will repeat a lot. Okay, so it's giant, it will keep on going as the size of the metal is. These metallic bonds are very, very strong. Okay, and what that means, because they are strong, they're very hard to break, or they require a lot of energy to break, and that means metals have high melting points and boiling points. Okay, so they have high melting point and boiling points. And you should also know that metals are good conductors of electricity because they have free moving electrons. Okay, so we have free moving electrons here. That makes them good conductors of electricity. And that is in both the solid state and the liquid state. So even in the solid state, these electrons are free to move. So if you are ever asked to define that or explain why metals are good conductors of electricity, is because in the solid and the molten phase, they have free moving electrons. Okay. You should also know is that they are insoluble. And what that means is that we can't dissolve it in solvents. Okay, we can't dissolve it in water. If we do add it to water and something does happen, it's actually a chemical reaction. It's not dissolving in there. Okay, it's in a reaction. It's not a physical property or physical change. Right, the other one that we have looked at is ionic bonding. So if you remember, ionic bonding or ionic bonds are formed between oppositely charged ions. So I'm just going to do it in 2D, but it is 3D. Okay, so I've just drawn the ionic bonds between them. The way we define this is it's the strong electrostatic attraction between oppositely charged ions. Okay, and again, when it comes to explaining the structure of this is again a giant structure. So this structure will keep on repeating, this pattern will keep on repeating. So we describe it as giant ionic structure. Okay, and again, we have very strong electrostatic attractions between the oppositely charged ions, and that makes ionic compounds have very high melting point and boiling points. Okay. When it comes to electrical conductivity, it doesn't conduct electricity in the solid phase because the ionic bonds keep the ions in fixed positions. Okay, the ions are not free to move when the ionic compound is a solid. If we dissolve or melt our ionic compound, the ionic bonds break and then the ions are free to move. Okay, so in the liquid or aqueous phase, ions are free to move. So that means we conduct electricity. Okay, that does not happen in the solid phase because we don't have ions that are free to move. And when it comes to solubility, ionic compounds are soluble in polar solvents. Okay, right, let's now have a look at the other type of bonding, which is covalent. And you need to know there are two types of covalent structures. I'm going to cover simple covalent first. Okay, so simple covalent, so we all know what a covalent bond is. It is the electrostatic attraction between the bonded nuclei and the shared pair of electrons. Okay, simple covalent applies to molecules. So for example, the ones that we've looked at are H2, O2, H2O, CO2, pretty much anything that we can draw the molecules for where we're trying to find the shape of the molecule based on bond pairs and lone pairs, tend to be simple covalent molecules. Okay. And what that means, within these molecules, we have very strong covalent bonds. So for example, in H2, we have a strong covalent bond between the hydrogen atoms. For O2, we have two strong covalent bonds. In H2O, again, strong covalent bonds, and within these as well, strong covalent bonds. Okay, so within these structures, we have strong covalent bonds within the molecule. Okay, but between molecules, okay, so for example, if I just draw this out, if I have hydrogen molecules, loads of them, like that, within the molecule we have very strong covalent bonds, that would require a lot of energy to break. Okay, so they don't tend to break, but between molecules, okay, we can have intermolecular forces, and we've covered the different types of intermolecular forces. And for this one, because we have non-polar molecules, the only type of intermolecular force we can have are London forces. So between molecules, we have weak intermolecular forces. Okay, and because we have weak intermolecular forces between molecules, that means that the melting point and the boiling point is very low for simple covalent molecules. Okay, because these intermolecular bonds don't require a lot of energy to break, we apply a little bit of energy and they will break, and therefore we're going to change state very quickly. Okay, so because of these weak intermolecular forces, we have low melting point and boiling points. Okay, just be careful when you are changing state, you are not breaking these covalent bonds, you are only breaking the intermolecular forces between them. Okay, in terms of conducting electricity, so they are electrical insulators, so they don't conduct electricity. And the reason for that is that they don't have any free moving electrons or free moving ions. Okay, so they are electrical insulators. And when it comes to the solubility of these, it can be hard to predict. We can assume that non-polar molecules are soluble in non-polar solvents, and we can also assume that polar molecules are soluble in polar solvents, but that isn't always the case. Okay, so it's hard to predict the solubility of these. So that is simple covalent molecules. So pretty much most of them will be adopting the simple covalent structure. Okay, these aren't giant structures. These are molecules by themselves that just have weak intermolecular forces between them. It's not a repeating pattern. It's not a giant structure. But we do get giant covalent structures as well. So I'm going to cover that now. And you should have done this at GCSE. So giant covalent structures. So again, they are going to have covalent bonds within them. The examples of covalent structures that you should have looked at back at GCSE is where you did the allotropes of carbon, and you would have looked at the diamond structure and graphite and graphene. Okay, these are giant covalent structures, and these all have covalent bonds within them, and these covalent bonds are very, very strong, and they're repeating patterns, so that's why they're giant. They're not just molecules by themselves with weak intermolecular forces. Okay, so these ones here are due to carbon. Okay, you can also have silicon and boron. So these three over here, so boron, carbon and silicon, will adopt giant covalent structures. Okay, and these are the examples that you need to know for carbon. In terms of conducting electricity, so diamond is not going to conduct any electricity because it doesn't have any free moving electrons. It definitely doesn't have any ions. But graphite and graphene do conduct electricity. And that is because they have free moving electrons or delocalized electrons, because not all of the electrons are used up in bonding there. Okay. And next one is they all have high melting points and boiling points. Okay, and the reason for that is that we don't have those weak intermolecular forces. We just have covalent bonds. Okay, graphite does have some weak intermolecular forces, but in terms of changing state, you would have to break the covalent bonds, which are very hard to break, and therefore these all have high melting points and boiling points. And they are all insoluble in solvents, in water. So yeah, none of them will dissolve in water. Okay, so that's the kind of different structures that you should be aware of. So there's metallic, ionic, and then when it comes to covalent, there's simple molecular, and then there's giant covalent. With giant covalent, only carbon, boron, and silicon will adopt that. Everything else should be simple covalent. Okay, so if you get a question where you are asked to compare a physical property, so either melting points or electrical conductivity or solubility of a couple of compounds. So let's say we're asked to compare a physical property between potassium bromide, and bromine molecules. Okay, the first thing you should do is identify what type of structure they adopt and then define the type of bonding. Okay, so as we know, potassium is by itself here, it's a metal, so therefore it's going to adopt metallic bonding. Okay, so what you should then do is define what you mean by metallic bonding. So it's the strong electrostatic attraction between positive ions and delocalized electrons. You then need to make a statement that this is going to adopt a giant metallic structure. Okay, and then let's go to KBr. So KBr, we got a metal and a non-metal, so it's going to be ionic bonding. So then define what we mean by an ionic bond. That is the strong electrostatic attraction between oppositely charged ions. You then need to say it will adopt a giant ionic structure. Okay, and then for Br2, because this is a covalent molecule, it's not anything from carbon, boron, or silicon, so it's going to be simple covalent. So simple covalent molecules. And then you would need to say what type of intermolecular bonding it has. So in this one, it is London forces. So you would say weak London forces, or you could say weak intermolecular forces. So weak London forces between molecules. Okay, and then depending on the property that you're asked to compare, so for example, if it's melting point, this one is going to have the lowest melting point or boiling point because it has weak London forces or weak intermolecular forces. So this one requires the least amount of energy to break. And then depending on the data they've given you, because you can't always compare, you don't always know which one's going to be higher out of these two. It is usually ionic, but it could be the other way around. Okay, so then make a comparison about the strength of the intermolecular forces, the ionic bond, and the metallic bond. If it's got to do with electricity or conducting electricity, again, you've got to discuss which ones have free moving either electrons or free moving ions. So yeah, they're the sorts of questions that you can get, and that is how you would answer it. So make sure before you even get onto the physical property, you state what type of bonding it has and what structure it adopts. And obviously if it's simple covalent, say that it has weak intermolecular forces between the molecules.